In this lesson, we'll be going over parallel circuits. Now before we continue into this lesson, I strongly recommend that you check out my last video on series circuits, as in this lesson I refer to that video quite often, unless you're good with series circuits, in which you can keep watching, but the link to that video is in the description. Anyways, back to parallel circuits. The best way to learn about parallel circuits is to compare it with series circuits. A great way to explain this is say you're going to the amusement park. When you arrive, you see that there's only one line. After you wait for your turn, you first go through the metal detector, then someone searches your bag, and then you show your ticket to prove that you paid for your trip. Doing this can be a long and tiring process, and can steal some of your energy that you want to put to riding all the roller coasters. This analogy sums up series circuits, as there's always one singular path in which current is moving, and constantly flowing through the wires in and out of the battery, while always having the constant strain of these three resistors. Now you would agree that taking away a resistor would overall result in less resistance in the circuit, but what if instead we added one? Then this would increase resistance in the circuit, correct? Let's use that same analogy of the amusement park for a parallel circuit with three resistors. Let's say you come back the next day, but now instead of there being only one line, there are now three different lines where the park is inviting people in. And instead of having three individual stations, all three are packed into one. And so you would first walk through the metal detector, hand the worker your bag for him to look through it, and they'll be done by the time you're done showing your ticket. And so what this shows is that for a parallel circuit, the current is being spread out through multiple paths, and in each path, that current only has to suffer the resistance of one resistor rather than three. So now this begs the question, does adding more resistors increase or decrease resistance? As in series circuits, the more resistors that you add, the more that you're increasing the resistance. And quote-unquote logically speaking, for parallel circuits, adding more resistors should increase resistance. Not true. Let's say that the park had 300 people lined up outside, evenly distributing these people along the three paths. Each station would have to deal with 100 different people, checking their bags, checking their tickets, making sure they walk through the metal detectors, whatever. What would happen if we removed this third path? The park closed it down. Now dividing those 300 people, each line would now have 150 people, causing more resistance and a longer wait time. But what if we instead added a fourth resistor, or a fourth line to get into the park? Now dividing that 300 by 4, there would be 75 people in each line. Or if there were 5 lines, there would be 60 people in each line. And so that is definitive proof that for parallel circuits, adding more resistors decreases resistance. Now let's get into solving a parallel circuit. For our given values, let's say that the total voltage of the battery is 250 volts. The first resistor, R1, had a resistance of 160 ohms, R2 had a resistance of 210 ohms, and R3 had a resistance of 125 ohms. For our formulas, there is of course Ohm's law, in which the voltage equals the current multiplied by the resistance. And then in terms of the Kirchhoff laws for a parallel circuit, first, the total voltage is equal to the voltage at each resistor. Similar to the Kirchhoff law for current in a series circuit, if you have the current at the first resistor, for example, it would equal the same current for the total current and at the current at the rest of the resistors, which is exactly the same for voltage in a parallel circuit. And then for finding total resistance, the formula is the same as the series circuit formula. However, it is the sum of the reciprocal of all the resistances. For parallel circuits, when more resistors are added, the resistance actually decreases, and so it is guaranteed that the total resistance will be lower than the lowest resistance in the whole circuit. So for this one, it would be lower than 125 ohms. And then finally, the total current equals the sum of all the currents at each resistor. So let's say the current was coming out of the battery, and obviously because this was a parallel circuit, not a series circuit, all the current is distributed in the three different paths. At this point, all the current is together, but once it reaches these points, the current splits up and goes to each individual resistor until it comes back all together at about this point. And now we're on our own. However, I did make it a little bit easy, seeing as I already gave the total voltage, which according to this formula is equal to V1, V2, and V3, which we do have to show in order to say how we found it. Now for the resistances. Of course, 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3, which would be 1 over 160 ohms plus 1 over 210 ohms plus 1 over 125 ohms. Now the easiest way to do this is to just put it into your calculator. I always use brackets just to be safe. You should be getting 0.019 ohms, which equals 1 over RT. And now to find RT, we can simply just find the reciprocal, making it RT over 1, which is just RT. And of course, we would have to do the same to the other side. So it would be 0.019 over 1. And when we do the reciprocal, we can see that it's 1 over 0.019. And so rounding to two significant digits, we can find that the total resistance is 53 ohms, which we can fill out for RT. And now we have found all of the voltages as well as all the resistances. All that's left is to find the currents. And going back to Ohm's law, the current equals the voltage divided by the resistance. And so each of them are 250 volts divided by their respective resistances. And so 250 volts divided by 53 ohms equals 4.7 amps for the total current. And then doing the same for the rest. I1 is 1.6 amps, I2 is 1.2 amps, and I3 is 2.0 amps. Now obviously to confirm, we can add all of these up. 1.6 amps plus 1.2 amps plus 2 amps equals 4.8 amps, which is different from 4.7, but this 0.1 amp deviation is negligible as it is a result of rounding, but nevertheless confirms that we have done all the right work and have found the correct answers. If you've made it this far into the video, chances are you're learning a lot and enjoy the content. So if you don't mind, consider subscribing, as it shows me that you like what you see, which helps me post more videos. Anyways, that's all for now. I hope you have a wonderful day.